my channel. In today's video, we will find a solution for 2017 and 2016 board question paper for the Unit 1 Electrostatics. First of all, we will discuss 2017's question paper, where there was only two questions from Unit 1. One was 3 mark and other was for 5 mark. So here we'll go with the 3 mark question. Two identical parallel plate capacitors A and B are connected to a battery of V volts with the switch S closed. The switch is now opened and the free space between the plates of capacitors is filled with a dielectric of dielectric constant K. Find the ratio of the total electrostatic energy stored in both capacitors before and after the introduction of the dielectric. This is a circuit diagram where A and B are two capacitors which are connected in parallel by means of a switch. A potential V volt which is given in the question is also applied across A and B. Now here we have to find the energy stored, the ratio of energy stored before the introduction of dielectrics and with dielectrics. So initially the circuit was closed. And then we will open the circuit. Now the capacitors A and B are charged. So first of all, we will consider the equivalent capacitance when there is no dielectric. So since the capacitors are connected in parallel, let the capacitance of A be C1 and let the capacitance of B be C2. Since they are connected in parallel, the equivalent capacitance will be equal to C1 plus C2. This is the equivalent capacitance of two capacitors which are connected in parallel. So the energy stored, the equation for energy stored in a capacitor is given by Q square by 2C, or we can write it as half CV square. Here I can write this as Q square divided by 2 into C1 plus C2. Instead of C, the equivalent capacitance can be replaced as C1 by C1 plus C2. Let this equation be 1. This is the energy when there is no dielectrics in between the capacitors. Now we are introducing a dielectric in between the capacitors. So C1 becomes KC1 and C2 becomes KC2, where K is the dielectric constant. Now the equivalent capacitance in this case is again equal to K into C1 plus K into C2. Where K is common, we can take it outside. So the equation becomes C1, K into C1 plus C2. Now we will find the energy stored in the case with dielectric. So U2 is equal to Q square divided by 2C. Or I can write Q square divided by 2K into C1 plus C2. Let this be the equation number 2. Where the equivalent capacitance C is replaced as K into C1 plus C2. Where K into C1 plus C2 is the equivalent capacitance when A and B are connected in parallel with a dielectric constant K. Now we got the equation for energy without dielectric and with dielectric. We will find the ratio by dividing 1 and 2. 1 divided by 2 implies U1 by U2, which is equal to Q square by 2C1 plus C2 into 2K C1 plus C2 divided by Q square. So while we divide the fraction, we can multiply by taking the reciprocal. So it is Q square by 2C1 plus C2 into 2K, that is the reciprocal of U2, 2K into C1 plus C2 divided by Q square, where Q square cancels, 2 cancels, C1 plus C2 cancels. So the ratio is K by 1 or K is to 1. So thus we find the ratio for the capacitors A and B which are connected in parallel. The energy stored with and without dielectric, that is U1 is to U2 is K is to 1. For more details on combination of capacitors, both series and parallel, and for the expression for energy stored in a capacitor, please check the description box. 5 mark question where it have 3 parts. The first part, derive an expression for electric field E due to a dipole of length 2a at a point distance r from the center of the dipole and the axial line. Second part, draw a graph of E versus R for R greater than A. And C, if this dipole were kept in a uniform external electric field E0, diagrammatically represent the position of dipole in stable and unstable equilibrium and write the expression for torque acting on the dipole in both cases. Here, the first part of essay is to find the electric field due to a dipole at its axial point. So, first of all, we will consider a dipole, where dipole is an arrangement of two equal and opposite charges which is separated by a small distance. So, plus q and minus q separated by a small distance 2l, where O is the midpoint of this dipole. Let plus q be at A and minus q be at minus B. Now we wish to calculate the electric field at the point P, which is an axial point of this dipole. Let the distance between midpoint and P be x. Now, since the total length is 2l and O is the midpoint, AO can be written as L and OB is also equal to L. Now, this P will have the electric field due to minus q as well as plus q, that is EB and EA. The direction of EB will be along the dipole moment and direction of EA will be opposite to the dipole moment. So the total electric field at P can be written as E. E will be equal to EB minus EA. According to Coulomb's law, the equation for electric field is 1 by 4 pi epsilon 0, the magnitude of charge divided by the distance, square of the distance between charge and the point. So first of all, we will find EB, that is the electric field due to minus q. So it is 1 by 4 pi epsilon 0 q divided by distance between minus q and p is BP. So it is BP square. Or I can write this as 1 by 4 pi epsilon 0 q divided by BP can be written as OP minus OB. So it is OP minus OB the whole square. Or EB is equal to 1 by 4 pi epsilon 0 q divided by OP is x and OB is L. So it is x minus L the whole square. So here we got an equation for EB. Similarly, we can write EA is equal to 1 by 4 pi epsilon 0 q divided by x plus L the whole square, where EA is the electric field due to plus q, x plus L is the total distance between plus q and P. So it is AO plus OP. So it is x plus L. So we got the expression for EB and EA. Now we will find the net electric field E. E is EB minus EA. So E is equal to 1 by 4 pi epsilon 0 q divided by x minus L the whole square minus 1 by 4 pi epsilon 0 q divided by x plus L the whole square, where 1 by 4 pi epsilon 0 into q is a common. Take it outside. So this becomes q divided by 4 pi epsilon 0 into 1 by x minus L the whole square minus 1 by x plus L the whole square. Cross multiplying this, x plus L the whole square into 1 minus x minus L the whole square into 1 divided by x minus L the whole square into x plus L the whole square. We can write this as q by 4 pi epsilon 0 x plus L the whole square minus x minus L the whole square divided by x minus L into x plus L the whole square. Here we can expand x plus L the whole square using the identity a plus b the whole square. X minus L square can be expanded using a minus b the whole square. So by simplifying, the numerator becomes q by 4 pi epsilon 0. The numerator becomes 4xl divided by A minus B into A plus B is nothing but A square minus B square. So x minus L into x plus L is x square minus L square the whole square. So this is the expression for equivalent electric field at the point P. Dipole moment of a dipole is represented as P, where P is the product of magnitude of any one of the charge and the length of the dipole. So P is equal to Q into 2L. Here we have E is equal to 1 by 4 pi epsilon 0 Q into 4XL divided by x square minus L square the whole square. We can rewrite this equation as E is equal to 1 by 4 pi epsilon 0 2QL into 2x divided by x square minus L square the whole square, where 4QXL is replaced as 2QL into 2x. Now this 2QL is nothing but P. So E is equal to 1 by 4 pi epsilon 0 2P into x divided by x square minus L square the whole square. So this is the expression for electric field at the axial point of a dipole. E is equal to 1 by 4 pi epsilon 0 2px divided by x square minus L square. Now the second part is to plot a graph showing the variation of electric field with a distance if x is greater than a or x is greater than L. That means here you are considering P as a far point. So if x is greater than L, in this equation L square in the denominator can be neglected because here you are considering x as a far point. So for x is greater than L, E becomes 1 by 4 pi epsilon 0 2px divided by x square the whole square, that is x raised to 4. We can neglect L square because here we are considering x as a far point or P is in a far point. So this can be written as 1 by 4 pi epsilon 0 2px divided by x raised to 4, where 1x in the numerator and denominator cancels and the equation becomes E is equal to 1 by 4 pi epsilon 0 2p divided by x cube. So from this equation it is clear that E is inversely proportional to x. So as distance increases, the E should increase. As distance decreases, the E should increase. So when we plot a graph to show the variation of electric field to the distance x or distance r, whatever it is, A is inversely proportional to x. So this will be the nature of the graph. Third part is to find the torque experienced by a dipole, where you have to diagrammatically represent it and also find the stable and unstable equilibrium of that dipole. So here we will consider a uniform electric field, where uniform electric field is always represented as straight parallel lines. So this is the uniform electric field. Here I am placing a dipole plus Q minus Q separated by a small distance 2L. Let this dipole makes an angle theta with the electric field. So let this be A, B. Now let BC be the perpendicular distance from the dipole to the electric field. So I can find sine theta. That is sine of angle theta. So this is a right angle triangle. Triangle ABC is a right angle triangle. So sine theta is opposite side by hypotenuse. So here the opposite side is BC divided by hypotenuse is AB, where AB is 2L. So BC by 2L, or BC, which is the perpendicular distance, is equal to 2L into sine theta. So here we find an expression for the perpendicular distance. This perpendicular distance BC is 2L into sine theta. Whenever a charge is kept in a region of uniform electric field, it experiences a force, and that force is equal to electric field into charge. So the force experienced by plus Q FB will be along the electric field, and force experienced due to minus Q will be opposite to the electric field. So let this be FB. So FA. So if you are considering this dipole, its opposite end, it experiences a force which is equal and opposite, and this couple of force constitute torque. So here we will find an expression for torque. Torque is nothing but force into perpendicular distance. Instead of force, we can write it as QE. Instead of perpendicular distance, we can write it as 2L sine theta, where Q into 2L is the dipole moment P. So instead of 2 into Q into 2L, we can write it as P. So the equation becomes P is sine theta, or I can write torque is equal to P cross E, where P is the dipole moment and E is the electric field. So this is the expression for the torque experienced by a dipole when it is kept in an uniform electric field. Now comes the stable equilibrium and the unstable equilibrium, where you have to consider three cases, where in the first case, let the dipole is parallel to the electric field. So if dipole is parallel to the electric field, theta is equal to 0. So if theta is equal to 0, torque is equal to 0, because torque is nothing but P is sine theta, where sine theta, instead of sine theta, we can write it as sine 0, so the torque becomes 0. As a result, this dipole never experiences a force, and that condition is known as stable equilibrium. So stable equilibrium is when the torque is kept parallel to the electric field. Now second case, if the dipole is kept perpendicular to the electric field. So theta is equal to 90 degree, sine 90 is 1. So in this case, torque is equal to PE. So when the dipole is kept perpendicular to the electric field, that dipole will experience a maximum torque. Now comes the third condition, is that dipole is anti-parallel to the electric field. That is theta is equal to 180 degree. So if dipole is anti-parallel to the electric field, then theta is equal to 180 degree, and that condition is known as unstable equilibrium. So for the stable equilibrium, dipole is kept parallel to the electric field, and for unstable equilibrium, the dipole is kept anti-parallel to the electric field. Choice for the essay question is also from the first unit, where the first part, use Gauss theorem to find the electric field due to a uniformly charged infinitely large plane thin sheet with surface charge density sigma. B part, an infinitely large thin plane sheet has a uniform surface charge density plus sigma. Obtain the expression for amount of work done in bringing a point charge Q from infinity to a point. Distance r in front of the charge plane sheet. Here, the first part is to find the electric field due to an infinitely charged plane sheet of surface charge density plus sigma, where we already did a detailed video. Check it in the description box. And now for the second part, you have to find the expression for work done in order to bring a charge from infinity to a point which is r distance from the thin sheet. Here we have a charged plane sheet of surface charge density plus sigma. And at the point P, the electric field E is given as sigma by 2 epsilon 0, which we already derived from the first part. Let V0 be the potential on the surface of the sheet and V be the potential at the point P. So, the rate of or change in potential dV is nothing but V0 minus V. So, according to the equation, dV is equal to E dot dr. I can write V0 minus V is equal to, instead of E, sigma by 2 epsilon 0. Instead of dr, it is a distance between point P and the sheet. It is nothing but r. So we got V0 minus V is equal to sigma by 2 epsilon 0 into r. V is equal to V0 minus sigma by 2 epsilon 0 r. This is the expression for potential at point P. What we have to find is the work. Work is nothing but V divided by charge Q0. Instead of V, we can write it as V0 by sigma by 2 epsilon 0 R divided by Q0, where Q0 is the test charge which is brought from infinity to the point P. So this is how we will derive the expression for work done in order to bring a charge from infinity to a point P, which is at R distance from a infinitely charged plane sheet of surface charge density plus sigma. For 2016, there were 3 questions, for 1 mark, for 2 mark and a 5 mark question. So here we will discuss the 1 mark question. A charge Q is moved from a point A above a dipole of dipole moment P to a point B below the dipole equatorial plane without acceleration. Find the work done in the process.
Work done is 0 because potential due to a dipole at its equatorial plane will be always 0. From the question itself, it is clear that A and B lies on the equatorial plane of the dipole. As it lies on the equatorial plane, the potential on B as well as A is equal to 0. As a result, work will be 0 because work is nothing but potential into charge. Since potential is 0, the work is equal to 0.
2 mark question. Define an equipotential surface. Draw the equipotential surfaces. First one, in case of a single point charge. Second one, in a constant electric field in Z direction. Why the equipotential surfaces about a single charge are not equidistant. Third one, can electric field exist tangential to an equipotential surface? Give reason. The second question is a question related to the equipotential surface, where we have to define what is meant by equipotential surface, and the first and second part is to draw the equipotential surfaces for the point charge and for the uniform electric field. Everything about the equipotential surface is described in another video where the link is provided in the description box, so you can check it out there. Why the equipotential surfaces are not equidistant for a point charge? Because as we move away from the charge, the electric field decreases. So as the electric field decreases, the potential also decreases. So the equipotential surfaces are not equidistant from a point charge. Third part, can electric field exist tangential to an equipotential surface? So according to the property of the equipotential surfaces, no work has to be done in order to move a charge from one point to another point on the equipotential surface. So if the electric field is tangential to the equipotential surface, we have to do a work which to move a charge from one point to another point on the equipotential surface, which is against the first property. That is, actually for an equipotential surface we don't have to do any work. So if the electric field is tangential, we have to do a work which is impossible. So electric field cannot exist tangential to the equipotential surface. 5 mark question. The first part. Use Gauss law to find the electric field due to a uniformly charged infinite plane sheet. What is the direction of field for positive and negative charge densities? Second part. Find the ratio of potential differences that must be applied across the parallel and the series combination of two capacitors C1 and C2 with their capacitance in the ratio 1:2, so that energy stored in the two cases become same. First part is to find the electric field due to a thin plane sheet. You can find it out in the description box. In the second part, there are two capacitors C1 and C2, where ratio of these capacitors are given, that is 1:2. So if C1 is C, we can write C2 as 2C because they are in the ratio 1:2. So one capacitor is C and the other capacitor is 2C. We have to find the ratio of potential differences when the energy stored in the parallel combination of these capacitors is equal to the energy stored in the series combination of this capacitor. So suppose we will consider the parallel combination. For the parallel combination, total capacitance will be sum of the individual capacitors. So C is equal to C plus 2C, which is equal to 3C. So energy stored Q or U is equal to half C V1 square, where V is the potential. Instead of C, we can substitute 3C. So U is equal to half 3C V1 square. Let this equation be U1. This is the energy stored when these capacitors are connected in parallel. Now we consider the series combination of the capacitors. For series combination, total capacitance 1 by C will be equal to 1 by C plus 1 by 2C, or C is equal to 2C square divided by 3C. Cross multiplying, C is equal to 2C square divided by 3C. C cancels, so C is equal to 2 by 3C. Here also we are finding the energy. U2 is equal to half CV2 square, where V2 is the potential difference in the case of series combination. Instead of C, we can substitute 2 by 3. So half 2 by 3 C V2 square. Let this equation be 2. U1 is equal to U2. We have to find the ratio of potential difference applied for equal energies. That is U1 is equal to U2, which is given in the question. So equating 1 and 2, 1 is equal to 2. It is given in the question. So half into 3C V1 square is equal to half into 2 by 3 C V2 square, where half cancels, C cancels. I am rearranged the equation, that is V1 square by V2 square is equal to 2 by 3 by 3. This 3 is taken into the denominator. So V1 square by V2 square is equal to 2 by 9. Or V1 by V2 is equal to root 2 by 3, or the ratio V1 is to V2 is root 2 is to 3. So this is a ratio of potentials that has to be applied in the series and parallel combination of given capacitors in order to make the energy stored in the combination equal. The old question for this question: if two similar large plates, each of area A having surface charge densities plus sigma and minus sigma, are separated by a distance d in air, find the expression for. First part, field at points between the two plates and on the outer side of the plates. Specify the direction of field in each cases. B part, the potential difference between the plates, and C part, the two capacitance of the capacitor so formed. Again, there is another part for this question. Two metallic spheres of radius r and 2r are charged so that both of these have same surface charge density sigma. If they are connected to each other with a conducting wire, in which direction will the charge flow and why? In the first part, here there are two plates given. One is of surface charge density plus sigma and the other is of the surface charge density minus sigma. We have to find the electric field at the region 1, region 2 and region 3. That is on the either sides of the plates and in between the plates. So if I am considering the region 1, for a positive charge, the electric field will be always directed outwards. That is E1 due to the plate A, which is charged positively, will be towards the left. That is electric field in the outward direction. Now E2 is the electric field due to the plate B, which is negatively charged. So for a negative charged plate, the electric field is towards the charge. So here E2 will be in the opposite direction of E1. So here in the question it is given that both the plates are having same surface charge densities, but they are in equal polarity, and area of the plates are also equal. Since the area and the magnitude of the charge are same, E1 is equal to E2, but here E1 is equal to negative E2 because they are in opposite direction. So the total electric field will be equal to 0. So in the region 1, the total electric field is equal to 0. Similarly, we will consider region 2. This is region 2. If we are considering region 2, electric field due to A. away from the plate because it is positively charged. Electric field due to plate B towards the plate because it is negatively charged. So it is EB. Here both the electric fields are in same direction. So E is equal to EA plus EB, which is sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. So E is equal to sigma by epsilon 0. This is the electric field in the region between the plate. And sigma by 2 epsilon 0 is the electric field due to a charged thin sheet which we obtained using the Gauss theorem, and that derivation is in the description box. So by adding both these electric fields, you will be getting the electric field in the region between the plates. So E is equal to sigma by epsilon 0. In region 3, there will be two electric fields. One is due to plate A, another is due to plate B. Due to plate A, this is the direction of electric field, that is away from the positive charge. Due to plate B, it will be towards the plate because the plate is of negative charge. So here also the total electric field is 0. So on the sides of the plate, the electric field will be 0. The electric field only exists in between the plate, and that electric field is equal to E equal to sigma by epsilon 0. Now, the second part is to find the potential differences between the plate. So, potential difference B is equal to E into distance. Here distance is D. So, instead of E, we can write it as sigma epsilon 0 D. So the potential between the plate is sigma by epsilon 0 into D. Now third part is to find the capacitance. Capacitance C is equal to Q by V. So C is equal to Q divided by, instead of V we can write it as sigma by epsilon 0 into D. Instead of sigma we can write it as Q divided by area. So C is equal to Q by Q D epsilon 0 A. Q cancels and we will be getting the equation as epsilon 0 A divided by D. So this is the expression for capacitance in between the region. For capacitance we can write the equation Q divided by V. Instead of V we can substitute this equation, that is sigma by epsilon 0 into D. Instead of sigma, substitute Q by A. So Q cancels. So epsilon 0 A by D, that is the equation for capacitance in between the region of two plates of surface charge densities plus sigma and minus sigma. For the second part of the question, there are two spheres. One is of radius r and other is of radius 2r. Here, the charge on where the surface charge densities are given as sigma. So the charge on the first sphere, let it be Q1, is equal to area into surface charge density. So here the surface area is 4 pi r square into sigma. Similarly, charge on Q2, that is charge on the second sphere, Q2 can be written as 4 pi. Instead of r, it is 2r. So 2r the whole square into sigma, or we can write it as 4 pi into 4r square sigma. So we got the equation for Q1 and Q2. Now we will find the potential on sphere 1 and sphere 2. So potential on the sphere 1. According to the equation of potential, it is nothing but 1 by 4 pi epsilon 0 charge divided by the distance. So V1 is equal to 1 by 4 pi epsilon 0. Charge is 4 pi r square sigma divided by the distance is r. Similarly, we will find the potential on sphere 2. So V2 is 1 by 4 pi epsilon 0. 4 pi, the charge is 4r square sigma divided by 2r. Here in V1 we will cancel 4 pi and r is cancelled. So the equation is r sigma by epsilon 0. In V2 again we can cancel 4 pi, r and r, 4 and 2 can be cancelled. So equation become 2 sigma by epsilon 0. So V1 is r sigma by epsilon 0 and V2 is 2 sigma by epsilon 0. what we have to find is that if these spheres are connected by a conducting wire, what will be or in what direction the charges will flow? That is a question. Charges will flow always from higher potential to lower potential. Here higher potential is V2 because it is 2R sigma. Lower potential is R sigma by epsilon 0. V2 is 2 times greater than V1. So the charges always flow from sphere 2 to sphere 1 because sphere 2 is in the higher potential, which is 2 times the potential of the first sphere. So that's all for today. Stay tuned for the solution of 2015 and 14. Thank you for watching me.